Welcome back to our YouTube channel. I'm Aaron from TCR, and today we want to talk about the progress we made with Project Poseidon over the last couple of months. This will be specifically about fire because we tested a lot with fire. For example, we conducted a hydrostatic test with the PVC tanks, followed by a high pressure thrust test, and finally rounding it up with a thrust test with a diverging nozzle. So we bought an air cylinder with 200 bar compressed air inside to use later on with Gap and Poseidon to fill in the pressurized air over a regulator. And to do some initial thrust tests, we decided to do them with fire, but if we wanted to do that, we need to verify that the PVC tanks could withstand 30 bar. So we did a hydrostatic test, which means that a lot of the volume of the tank is actually water, so not used, and only tiny volume is air, which is then pressurized. And we tried that out with all three tanks, and the first two tanks were too leaky. So water was pushed out of the seams, and we weren't able to get good measurements. But the third tank, so the tank we currently use as the air tank on fire, worked fine.
So the main valve can open 30 bars and the tank can withstand 30 bar. So we're gonna try 32, 34. Let's just see.
Withstood 30 bar and in the end even like 32, so we knew it's safe to continue to do the thrust tests. Following the successful hydrostatic test, we felt comfortable moving on to the high pressure thrust tests. We used for that our usual setup, except for the air compressor we used our high pressure air cylinder. Just to verify that everything was comparable, we did the 8 bar test. Here you can see the 8 bar test with the air compressor, and here you can see the 8 bar test with the air cylinder, and everything looks fine, so we were good to go. Following that, we continued with our main objective to test with higher pressures. What you can see here is the weight graph for 16 bar, and the important line is the green one, weight both, which is this here. And overall we had more thrust than the 8 bar test, which was expected. And continuing now with the 25 bar test, which you can see here. 3, 2, 1, fire. We have an initial thrust of around 6.5 kilograms, and the most important point is that we have a negative weight, so the rocket would actually have lifted off if we didn't hold it down. At 30 bar and above, we realized something interesting. This is the plot for the 25 bar test, and if we now go to the 36 bar test, you can actually see that the thrust declined. We think that this has something to do by an underperformance of the valve, because the pressure difference over the valve is substantially higher at this test. Now let's compare this measured data with our simulation, and keep in mind that this here seems to be steady around minus 1.7 kilograms or something like that. If we now switch to our model and choose force, which is the simulated force which should be measured by the load cells, this is also around minus 1.7 kilograms, so that matches. Now let's look at the simulated data for the 36 bar test, as you can see here. We kept everything else the same, and so you can see that we could expect a measured force of around minus 4 kilograms to minus 3.5 kilograms. If we look at the measured data, we have around plus 1 kilogram. So there's a huge difference there.
As you can see here, the water exhaust has quite a significant angle to the thrust axis. In this half section you can see the straight nozzle we started with. This is problematic because there's a difference between the static pressure of the existing water and the surrounding atmosphere. This results in the angles that we saw before. Additionally, there are general losses due to abrupt transitions in the flow line, for example at the inlet of the nozzle. If you look at normal rockets, all of them have a Convergent-Divergent nozzle. This is to expand the exhaust gas to ambient pressure. This is also nicely explained in a video by Charlie Garcia, which is linked down below. We thought this was applicable here too, so we tried it out without really calculating it. We took a reamer and created a converging section at the inlet and a diverging section at the outlet.
2, 1, fire. Let's talk about the test results. Here you can see the plot of the weight for the 20 bar test with the converging-diverging nozzle, and the thrust is considerably more than we had with the normal 20 bar test with the straight nozzle. The same goes for the 25 bar test you can see here. If we now take this data from the 20 bar test and try to reconstruct it in our simulations, we need a higher thrust efficiency coefficient of 0.9, and then you can see that this data matches this data pretty well. We can see that we have a peak thrust of around 7.8 kilograms. If we now do the same with the 25 bar test, we can see here with the same 0.9 thrust efficiency coefficient, we get this thrust of 8.7 kilograms, and now look at the force to compare the measurements, and here you can see that this simulated force and this measured force matches as well. We think we are going in the right direction, and if we do the math, we think we can get an even better thrust efficiency coefficient. Also, this would enable us to write a better simulation and to better characterize losses which are generated at the nozzle. So overall we can get even more thrust than discussed earlier.
Now let's take a look at our plans for gap. With the simulations we optimized the design for gap, reaching a tank diameter of about 80 millimeters and the same volume of tank for both water and air of about 4 liters. This concludes in a rocket height of about 2.1 meters and a dry mass of about 1.5 kilogram. The gap tanks will be made out of carbon composites, and we will machine fittings like these out of aluminum or steel. Additionally, some parts are 3D printed, like the battery holder. If you want to learn more about the design of the gap tanks, feel free to check out my blog article, which is linked down below.
We are also quite active on the software side. For example, we did a verification test for our rotational math, as you can see in this video. We already analyzed the unstable case, and our rotational model and reality matches pretty well. I am currently working on analyzing the stable case, and here you can see a code extract from my Quaternion library. And we are also hard at work learning control theory to design the control loop we need for gap and then later on Poseidon. I am also working on the code base for gap. This, for example, includes a major overhaul of the communication protocol between the laptop, so the ground station, and the rocket, to make it just more solid. We had a lot of successful tests over the last couple of months, learned a lot and gathered a lot of data, so we are now feeling comfortable moving on from FAR to gap. This currently means for Finn that he is in the final design phase for gap, and on my side I'm hard at work writing the code we need for gap.
After we finished the design for gap, the next step will be the fabrication of the first carbon composite tanks used for testing.
Thank you for viewing today's video all the way to the end. Hope to see you again in 2 months. Bye.